Machine learning has a reputation for being sleek, autonomous, and lightning fast. But for the analysts actually doing the work, the day-to-day process involves a high degree of manual friction. The daily grind often collapses into an avalanche of manual spreadsheets and repetitive tasks. Data scientists spend hours scanning raw rows of data to spot patterns. They sketch out basic assumptions, write the same boilerplate code for every new project, and eventually resort to screenshotting accuracy tables to build a static report. Automation tools like AutoScaler or FAML were designed to bypass this busywork, yet they often hit a major roadblock. They operate as black boxes. These systems excel at optimizing a mathematical metric to find a winning model. However, they lack the capacity to explain why that specific model won using plain human language. While the industry has automated the mathematics of data science, it has largely left the actual scientific method, the reasoning, the hypothesis testing, and the narrative, to be handled manually. Take the IRIS dataset, 150 rows of data. The goal? Generate a publication-ready research report in under 10 seconds. The clock starts right now. Stage 1. The system categorizes the task and snaps into focus. Stage 2. It branches out, generating 5 natural language hypotheses. By forcing the system to state its assumptions up front, the pipeline establishes a specific, testable theory before a single model is ever trained. This pre-processing phase anchors the machine's speed to the logic of the scientific method, ensuring the resulting code serves a specific research question. In Stage 3, 4 distinct machine learning models, Logistic Regression, Random Forest, XGBoost, and LightGBM, race across the axis, training simultaneously. Logistic Regression surges to the top, locking in a final accuracy score of 0.9733. Stage 4 calculates feature importance to isolate what mathematical variables drove that high score. The output shows 2 physical traits, petal length and petal width, expand to take up 83.1% of the predictive signal, explaining the model's accuracy. The pipeline takes these hard numbers and cross-references them back against the 5 original natural language hypotheses it formulated at the start of the test. Finally, in Stage 5, the pipeline compiles the training data, the feature charts, and the validated hypotheses into a structured 7-section PDF research document. This unified output connects raw code and isolated mathematical metrics into a single reasoned explanation of the data. The timer slams down at roughly 7 seconds. In that brief window, the system moved from a raw CSV file to a finished report. The validation scorecard slides into view, revealing that 3 theories were fully supported, 2 were partially supported, and 0 were refuted. This allows a single analyst to apply a rigorous, audit-ready framework across dozens of datasets in a single afternoon, without the workflow breaking down. But the most significant detail of this experiment isn't what the software processed, it's how the software was actually created. This entire autonomous research loop, every line of Python and every automated test, was researched, coded, and published by an artificial intelligence. It originates from an AI agent named Neo. A tool built to eliminate manual keystrokes from data science was itself developed without a single human keystroke. We have demonstrated that the loop of hypothesis, experiment, and documentation can be fully enclosed within a single autonomous system, allowing the research process to continue even after the human researcher steps away.